All right, so today is the 6th session, so welcome everybody. Just as a quick practical thing, next week will be the last session. As I said in my email, I don't plan to share that recording immediately, mostly because a lot of the things I'll be showing is ongoing work, and so just don't want to put that on the internet immediately. If there's next week, if there's any things you find really exciting and you want to work with us, just let us know. I'll say it to everybody again next week as well. And then today we're talking about haploblocking and haplotyping. So in the last 2 sessions, we've been looking at parent-child errors, and actually I'll just make my screen bigger. So we've been talking about parent-child errors and linkage errors, but that was always for single markers, so that meant single SNP in our case. And although that with the linkage errors we've been taking into account flanking markers, at this point we were always looking at errors that were occurring for a single marker, or whether they were correctly called or whether they were correctly in the map. So today I'll talk about haploblocking and haplotyping, which is group markers. So now we're going to really start looking at SNP markers as a group. And I'll be talking about how we get to our haploblocks and our haplotypes, and some common issues when I'm looking for errors. So as part of the whole workflow that the paper described, we're at this lower part here of the workflow now. So as I said last time, these two will probably take most of the time. Those are the ones that I went over in the last 2 sessions. And then today I'll talk about how we determine haploblocks and haplotypes, and then looking at the errors in them. And as you can see, it's actually very similar to the single marker level. We'll first look at inconsistent errors and then at consistent errors. And so the way we do it is very similar as the one with the single markers, but we first need to get our haploblocks and haplotypes. Now I wanted to quickly go over 1 or 2 things from last week. So I was mentioning last week that when looking in Visual FlexQTL and you're looking at all your marker names here, there's nothing in Visual FlexQTL telling you which chromosome you're on. So I got an email from Sujit asking me if it would be a solution to just add the chromosome number in front of the marker name. So in this case, that would be, I think this is chromosome 1, so it would be 1 underscore or 1-5444. And that way, when you're looking at a marker, you can very quickly see which chromosome you're on. And I think that's a great idea. I haven't really used it, so the only thing I was thinking is that might be a very small downside is that I am very used to just copy pasting a cell from Excel with the SNP index into Genome Studio. Once there is a linkage group in front of it, I won't just be able to copy paste it. I will either have to just select the number of the index and not the linkage group, or after I copied it into Genome Studio, I have to delete the 1- or the number and the dash, which right now at this point, I don't think it's a lot of work. I do know that just from experience with doing a lot of these things, a lot of the time, even small little actions that don't take up a lot of time, a single time, if you do them thousands of times, they can add up and they can make things slower. So that might reduce slightly the speed of which you're looking at SNPs, or you need a few more actions. On the other hand, looking up which chromosome you're on in Visual FlexQTL also takes some time, so I think they might negate each other, and I think it might work really well. That said, I think we should only then use it for the double recombination checking, because for all the other steps I've been showing, it's much easier to figure out which linkage group you're on, or it doesn't really matter because you're just looking at an individual marker and now it's flanking markers. And so at that point, I wouldn't use the chromosome number in the name. And the other thing you need to be aware of if you're doing index matching is that if you start using different names for your markers, that it might not be as easy to pull up information from one file to the other. There's also ways around that by keeping both names somewhere in the data file, etc. you can work around it. So overall, I think it's a good idea to make it a bit more clear where you are on the chromosome level when looking for double recombination. And then there was a question in the chat, and for some reason my chat window, I didn't get the newest messages. It was just stuck on a single message. But there was a question if the multi-locus SNPs that I talked about, so the SNPs that can be put on that are mapping to multiple locations in your map, if they have normal intensity patterns. And the question there is, overall, they don't really have the normal intensity patterns with the AA all on one side and the BB on the other side and the AB in the middle. So these are two plots for multi-locus SNPs that I've seen the most. One is where everything is squeezed together, and that can be explained if the second locus that you're looking at is most of the time homozygous. If the second locus is most of the time BB, then while BB individuals will also have that second locus bind and still have more BB, and so they will still look like BB. But individuals that are AA for the first locus and BB for the second locus will now have a mixture of A's and B's, because that second locus also amplifies, which makes the A cluster move closer towards the B position, and the same is true for the AB. So a multi-locus SNP can have your cluster squeezed if only a few individuals segregate for the second locus. Now, if a lot of individuals segregate for both loci, you get something that looks more like this, where individuals that are AA for both loci will still be in the AA spot, and individuals that are BB for both loci will still be in the BB spot. But then individuals that are AA and AB for the other locus, or AA and BB, they will start moving out and form extra clusters. So you'll start seeing all these extra clusters. Now, given that this clustering didn't lead to a lot of parent-child errors, at least, it means that overall our calling was relatively okay. But then when there's two loci involved, you'll get issues with the map, because they're segregating based on which locus is informative for this marker. And so they'll segregate based on. So they'll segregate according to one locus in one spot for some families, and segregate for the other locus in other families. And that's why you get double recombinations. And then talking about haploblocking and haplotyping. So just to begin with, what's a haploblock? What's a haplotype? Well, a haploblock can be seen as a discrete chromosomal segment that is co-inherited over generations. And I put off selection in brackets because most of the time for our crops, we are only interested in selected individuals. There's a lot of seedlings generated every year, and most of those seedlings get thrown out. And so it doesn't really matter where they had recombinations, because they don't stay, they leave our data sets. So it's a part of a chromosome that gets inherited, well, that is inherited over generations, and so over which we don't see any recombination. And that chromosomal segment is then characterized or assayed by multiple markers that are on that segment. So in this example here, a haploblock would be containing multiple markers, and in our case here, haploblock 1,1, which means in the way that we name our haploblocks, it means the haploblock on the first chromosome, and then it's the first haploblock on chromosome 1. So that one would here then consist, that chromosome segment would have 5 of our markers on it. So that's a haploblock, and then haplotypes are the alleles of the haploblock. So they're the variants of each segment. And so it's a specific combinations of our alleles. So if we again look at this example here, then our haplotype, which is the haploallele idea, we would give those numbers, and here are 4 numbers, 4, 5, 6, and 7. So 4 haplotypes, and haplotype 4 corresponds to a B allele for the first marker, then an A allele for the next 3 markers, and then a B allele for the last marker. And so different haplotypes stands for different combinations of our individual alleles for our individual markers. And so you can also see that some haplotypes are more similar to each other than others. Then why are we interested in haploblocks? Well, one, most of the time it will reduce our computational time, especially once we get to a large number of markers. If we have thousands and thousands, maybe even 10,000 of markers that we're using, that's a lot of markers that our software has to look at and do association analysis with, or look for structure, etc. in our population. So by using haploblocks, we combine 5-6 alleles into a single one, which means it's only a single one that, or a single region or a single marker. It looks like a single marker that the computer needs to take into account. So you can go from 4,000 or 5,000 markers to maybe 1,000, and so it can reduce your computational time. It increases informativeness, and it's not fully increasing the informativeness, as all the information was already there on the single marker locus. It's more that the information becomes more readily available and more easily interpretable. For example, when you're looking at alleles that are traced through a pedigree, here on the top, if we were working with SNPs, both parents are heterozygous AB and the offspring is AB, then at this point there's no way of telling where the A in Kit's orange red in this offspring came from, whether it came from Delicious or Cox. And the same goes for the B allele. So it would be hard to trace unless we look at flanking markers and we look at maybe more generations or SIPs and so forth. Whereas if we work with haplotypes, which are multi-allelic, which act as multi-allelic markers, we have still 2 heterozygous parents and a heterozygous offspring, but now it's very clear immediately that the 6 must have come from Delicious and the 4 must have come from Cox, because the 6 doesn't occur in Cox and the 4 does not occur in Delicious. And so there's a lot of other applications that we can do with haplotypes that make a lot of our data more easily interpretable and our analysis more easy. So, and I'll be talking about that next week a bit. So that's one of the reasons why we use haploblock. And also, when we are creating our haplotypes and haploblocks, sometimes we find additional errors. So it actually helps us also to create a better data set. So how do we make our haploblocks? How do we know which markers are grouped together and which ones are not? So the 2 ways I've done it, 2 main ways, are either based on linkage disequilibrium or based on historic recombination. There are other ways to group your markers, for instance, using positions, but I'll come back to that. We shouldn't really call these haploblocks, at least not based on the definition I gave before. So if we're talking about linkage disequilibrium, the advantage of that is we don't need a pedigree, and in most cases a physical map is sufficient. And when I say we don't need a pedigree, it means we can do this for a more wider germplasm in which our individuals might be connected to pedigree, but we don't know it because there's many generations between them, and most of the time we don't have access anymore to those previous generations. So we lost that information, and so it's using linkage disequilibrium, which is if 2 markers would be segregating independently, so the blue and the yellow, green locus here, and for the blue locus, there's a 50% of A alleles in the population and 50% of B alleles in the population, and the same goes for the green marker. Then we expect that the combination of 2 alleles over the 2 loci would be about 25%, or 0.5 times 0.5. So we expect it to be the multiple of the 2 independent frequencies. But when markers are linked, that's not the case. When markers are linked, it might be that A and A occur almost all of the time. So that would mean that the alleles at both loci are strongly correlated and they're highly linked. And so that's when that happens when there's linkage disequilibrium, which means that well, basically it's kind of the correlation between the 2 alleles. It's a simple way to put it. And so if 2 markers are if you know one allele and you can readily determine what the other allele is for the second locus based on the allele of the first locus, that means there's a high correlation. That means that they're probably strongly linked, and that also means that over many generations these alleles have been inherited together, and that there's been very little recombination between those two markers. And as such, those would be on a chromosomal segment that is co-inherited over many generations. And so there's a way to do this if you're working with this kind of populations. And I've used HaploView before. I'm not going to go into too much detail, but this picture is one chromosome, and it shows how correlated alleles are between two loci. So you see all these little squares, and it's slightly easier to see here where you have like this one individual red square, but there's all these squares all across this pyramid. And what it means is the color gives an indication of the correlation between the alleles of two loci. So in the case of this little dot, it would mean the correlation between a marker that's all, if I go diagonally all the way to here, and then I think I was using this one, so it would be also going over there, and so it would be the correlation between alleles from markers in this region and this region. And so of course, as markers are closer here, then the correlation might be much higher. And if we look at this plot, we can see that there's blocks, little red pyramids of markers for which the alleles are highly correlated, or where alleles are in linkage disequilibrium. And so those would form haploblocks. Those markers would be grouped together in a haploblock because their alleles are highly correlated. I'm not going to go much more into detail about HaploView because it's not the way we've been doing it in RosBREED. In RosBREED, we've been using historic recombination. So as I've been showing last week, we can, with Visual Flex QTL, we can follow through generations where recombinations occurred. We used it last time to see double recombinations, but we can just also see the normal true recombinations that are occurring. And so we can go through our pedigree and figure out where recombinations have happened and where they have not happened. And so any markers in between which no recombination occurred, we could then put together in a haploblock. Now, if we're using Visual Flex QTL, we need a genetic map and we need accurate pedigree information. Now, those are two things we've been fixing and curating in all the previous steps. So by the time we get to our haploblocks and haplotypes, you can be pretty convinced of our pedigree and our genetic map. So we have that. And so, as I said, then we are looking for markers for which no recombination occurs, at least for selected material. And then I'll mention the position-based one. It's, like you said, it's probably better not to call them haploblocks, but rather aggregate blocks or some other name. And that is because if we base our grouping on position, even if markers might be closely positioned together, there might still be recombination between them in our selected material. But there are some other advantages to doing it also position-based. One is if we use our genetic positions, at least then we say we group markers for 1 centimorgan. Then if we do QTL analysis, at least our resolution is high enough. Because when we are doing these haploblocks based on recombination, sometimes you'll see that you get haploblocks of 5 or 10 centimorgans long. And if you would use those for QTL analysis, well, that would mean that you don't get a better resolution than that 10 centimorgan. And you might have a lot of seedlings that are recombining within those 10 centimorgan, but if you grouped all your markers, you're not going to see that properly. So in that point for QTL analysis, it might be better to just, rather than looking at historic recombination, it might be better to look at a certain intervals to group your markers. And then the other way, what one can do is using physical positions, and many of our arrays have been designed to do that. They call them focal points, in which, as you can see here on the left, is when if you look at a chromosome, there's focal points of a specific distance. And for the Apple 20K array and the Cherry 6+9K array, it's 10 kb. For the Apple 8K, it was 100 kb. But it would mean they selected SNPs in an interval of the size, so in this case 10 kb. and then there were no SNPs in between. So all our SNPs are then grouped physically very close to each other, which is reducing the chance for recombination and allows us to group all these markers that are in a small group here together to make multi-allelic markers from them, or aggregate blocks or haplotypes. And I think overall, the distance here between two groups is then set, I think in the design was set to about a centimorgan. I think for the cherry 6+9K array, we intended to have an interval of about 0.6, 0.7 centimorgan. And then we had an interval of 10 kb. Unfortunately, even if we moved our clusters around a bit, it was hard to find always enough SNPs in a single region. So we ended up doing as much SNPs as we could in a focal point for the cherry array, and then having a few SNPs in between just to make sure we have adequate coverage of every region. But so grouping SNPs in different ways based on position is also an option. Then how do we do it? When we do it with historic recombination and visual flex QTL. So if you remember last week's session, we can see the recombination. We can see where a chromosome came from, and blue meant that for this individual, it's in this individual. It came from Idaret, and in Idaret, blue means it came from the father of Idaret, whereas yellow would have meant it came from the mother of Idaret. And then as you see changes from yellow to blue, that means there's a recombination, and in visual flex QTL, they're indicated by a stretch of orange. So an orange means a recombination. And so how then do we know where to split, or how does visual flex QTL know where to split our markers or our block? Well, it looks at the last marker with a 0. So and it says this is the starting position of my recombination. And it looks at the first marker with a 1, or the last position of the recombination. So the recombination occurs over this interval. But for some of these markers, it has these S0s or S1s, which means there is some evidence that it's probably coming from the null chromosome or the 1 chromosome. And so it is using that information into account. And given that these are two nulls, it's saying most likely my recombination happened in here. And then if then visual flex QTL looks at what is the position of this marker, and this happens to be 14.21. And it looks at the position of this marker, and that is 17.08. And so then it says, well, the middle of this interval is 15.645 centimorgan. So it puts the recombination right in the middle of the interval. And then as you go and look where the other markers are positioned in this interval, you can see that this marker is at 16 centimorgan. And so that means that, well, if 15 is the middle, that means the recombination happened between this marker and this marker. So it puts a splitting point for the haploblock right here. So it means that if this would be the only recombination that we see, then everything left of this splitting point would be one haploblock, and everything right of this split would be another haploblock. Now, obviously, there's more than one recombination happening in our germplasm. So if we look at the broader picture here, we can see there's, in this instance, 6 recombinations. So there's going to be multiple splits. And so visual flex QTL at that point starts with the smallest interval. So that's why this is a 1, because this interval happens to be the smallest one, and it will put a splitting point right in the middle, which is this black line. And then it will go to the next smallest one, which is this recombination here, and it will determine again a splitting point for this one, and it continues to do that for all the other recombination. And then when it gets to 6, which has a pretty wide recombination interval where it's uncertain where the exact recombination exactly happens, it will see that it already introduced a splitting point because of recombination number 3. And because it already introduced a splitting point before in this recombination interval, it's going to decide that it does not need an additional one. So it's not going to look for the middle of this interval, because it's saying it doesn't know where it is, and so any splitting point is a good splitting point at that point, and so it decides to keep the splitting point as it is here, even though it's almost at the end of the interval. So I do want to point out that it chooses the middle of the interval, and that's not always true. And then secondly, as I've been saying here, once there is already an interval or a split here, it will not introduce an extra one, even if it's really at the side. So those are two possible places where errors can occur, given that it's not sure that it's really in the middle here, and it's definitely not, and it's also not sure that it's really near the end here. So there are some possibilities for errors in determining which markers are grouped or not. So if we want to go and use visual FlexQTL to determine our haploblocks, we need accurate phasing. We need to be very sure which alleles are on the same one homolog and which alleles are on the other homolog. And so before, I've been saying when we're doing our error checking that FlexQTL checks over generations. So even if you have a parent missing, but you have the grandparents, or you have the parent and the grandparents missing, but you have the great-grandparents, that at those points, that it's still worth to include those links, even though you don't have the intermediate ancestors or the intermediate family members, because FlexQTL will look for errors over them, and it's really useful to find extra errors. On the other hand, when we're doing phasing and we don't have genetic data for these individuals, and these individuals are not really represented well enough, then determining the haploblocks might become an issue. So any intermediate ungenotyped progenitor needs to be removed from our data set. We're not going to actually remove it. We're going to just cut the link for that individual with its ancestry so that it becomes a founder, because it's not an issue for founders. Founders are individuals who we don't have parent information for. You can also keep intermediate ancestors as long as we have enough offspring genotyped, because if we have enough offspring genotype, we can get a good idea of what the phasing should have been like, or what the alleles should have been like. But that's only if you have enough offspring. Then secondly, visual FlexQTL needs to know which individuals are important and which ones are not. So which ones are, in our case, selected material, and which ones are not. And even we probably, or if you know your germplasm, you can probably just see it by name, which ones are cultivars or selections and which ones are just seedlings, but visual FlexQTL cannot. And unfortunately, there's not an easy way where you just add a parameter to the file where you list which ones are selected or not. So visual FlexQTL has its own way of determining whether something is selected material or not. And what it does is saying, well, if it's selected material, if it's important, it must have had some offspring, whereas seedlings, you don't use those as parents, so they won't have offspring. So FlexQTL or visual FlexQTL will assume that anything with at least one offspring in our data set is selected material, and anything without offspring is unselected material. And so we'll need to adjust our database slightly, just to our data set slightly, just so that we can accurately determine our haploblocks. So how do we do that? If we go, I've shared some files with you in the haploblock determination, because we're looking at how to know which markers to group. So we're determining our haploblocks. There are some FlexQTL input files, and in those I have two data files. One is the start one is the one that we would start from after checking all our double recombinations, and when we figured out that our data set is good enough to go on to haploblocking and haplotyping. So if I open that file, shouldn't take too long, then it just looks like any other data input file for FlexQTL. And so now we have to go and look at individuals that don't have any data, because those might be ungenotyped intermediate progenitors. So a whole line of dashes, well, here's a little bit of data filled in, but here is a lot of individuals with no data. those were all dummy individuals that we introduced just so that FlexQTL have 2 parents, so they had all missing data. But over time, some of it got filled in because, well, one, we know now what this parent is, and we also know how these, even though this is made missing now, we did know the ancestors. So given that this wasn't a genotype intermediate parent, but we do know the ancestors, it's good that these are now missing, because we that way we're not removing our intermediate ancestors from our data set, but rather we're just cutting the ties with everything that is further up in the pedigree, which is enough to get accurate phasing. And I believe that in this file there are no intermediate ancestors, but I can show you. There's a few that will come back. Here is Venda is one that we actually do know the 2 parents of, but we've also made it missing. And the same goes for Ruben. We know the parents, we've confirmed the parents, but we don't have Ruben, nor do we have some of the parents. So we've cut the ties with the rest of the pedigree here and made them missing. So that's one of the 2 things you need to do. Now, the second thing you need to do is make sure that all your selected material has offspring in it. And although Visual FlexQTL cannot read the nuisance variable or anything else for that, I made this nuisance variable so that anything that is selected material here has a 1, whereas everything that is just seedlings has a 0. So by filtering this column for 1, I get all my selected material. So I can just copy that list by holding Ctrl-Shift and pressing down. That way I select everything, I copy it, and I'll just copy this in a new sheet. And then I want to know how often each individual is used as a parent. And so I'll unfilter here. So, though I don't think it's needed, but just to be sure. And I say here, I want to count if, and I want to look in my 2 parents list. So these are the 2, well, mother and father for each individual. So in all of those individuals, across all those individuals, I want to count. It's not doing it correct. I want to comma first, and then I want to count how often Akani is occurring in that. And if I look at that, I see that Akani is occurring 2 times. So if I then drag this from here all the way to the bottom, I can already see that there are some selected individuals that have 0 offspring. So I can, again, use a filter to figure out which these individuals are. And so here I have my list of individuals that don't have any offspring, but that are selected material and that I want to take into account for haploblock determination. So I then can just paste this here, and once I unfilter this, we'll have the list completely here. And as you can see here, it's about 69. It's 69 individuals that don't have any offspring in our data. So the easiest way to make them have offspring in our data is to just create some dummy offspring that doesn't really exist, that is using these parents, or that have these parents as these individuals as parents, so that these individuals get offspring in our data. And so if, well, in this case we have 69, so don't need to do that. If I hold down Shift, I can just start selecting individuals, and I'll just count all the way down to 35. And if I, let me think, and then, so I have 35 individuals selected. So those are my first half. Everything below that is my second half. So if I cut those, Ctrl-X, and then paste them, then now I have here a list of 35 crosses. That will give me 1 dummy seedling that will then make sure that all these individuals have at least 1 offspring in the data set. And given that FlexQTL always wants 2 parents, for this one, I'll just copy any of the individuals here. And then I can just select all of this. And at the bottom of my data set, paste these in. So these become the parents. And then I just call these dummy, and I'll call it dummy for haploblocking 0, 1. And if I make this a bit bigger so that you can see, then full name, and then you can see that I just now created 35 dummies, for which I still need to fill in all the other columns as well. So this is a nuisance. So it doesn't, and this is a phenotype, but it doesn't really matter what's there. And other than that, I just need missing alleles for the whole individual. And I know that this individual here does not have any alleles in the data set, so I'll just take that one and I'll copy paste it and then select everything and drag it down all the way to the bottom. And at that point, I've created a data file that now has, for which all my selected material has at least one offspring in the data set. And as you can see here, where it's still counting, if I press on this, there's no zeros anymore. So all my selected material truly has at least one offspring in my data set. And then I go ahead and save this file. I'm not going to do that because I already made that file here. And that's this file. We can open that just to show you. But it's the same file as I had before that I created just now. And I've been using that to run some FlexQTL analysis to determine the haploblocks. So as you can see, again, I created here 35 dummy individuals. So the next thing I need to do is run a FlexQTL or a visual FlexQTL analysis. And so I do that, as always, by creating a new project. If I run this, I would probably go, it's going to be in, for me, I would put it in a haploblock determination folder. So I choose my folder, I choose the name, so I can call this haploblock determination. And then I use my input files, the parameter file, and I'll come back to the parameter file. And then otherwise, it's just the map file that I had from my last run, looking at double recombinations, and then the data file I just created. And I would say, okay. And then I create a FlexQTL project, and then I need to set a few parameters. I have to make sure that certain parameters are set a certain way so that I can get the right output. So the parameters I need to set are these 5 parameters. And so the ones you can see here at the front, like the red print or the MSEC delta, is how they are in the text file. So if I open the text file, and we go all the way to the bottom, you see here skip sample markers. You can see here red print. You can see marker block and so forth. So this is the name as they appear in this parameter text file. Now, most of the time, I change my parameters in Visual FlexQTL directly because I can do that too. And so they have sometimes slightly different name. Skip sample markers is still called the same, except now has some spaces in here. Red print is called print output information, and I think that MSEC delta and delete DR are these two here, and a 1 means that they're checked. So what some of this is doing is making sure we get all the output we need, and then delete double R. DR means delete double recombinations or delete double recombinants. That is only for singletons. As I said last time, there might be a few that remain, and probably you've considered them to be true, but for haploblock determination, it's probably better to just not take them into account right now. It's at least what we've been advised also by Eric van der Weg. So we've been doing that, and that seems to be working pretty well. So these are the settings we've been using and that we need to get certain output files. And then we would run Visual FlexQTL. And that would take probably about an hour. So rather than doing that, I have a project made, which was under FlexQTL results, haploblock determination CRS. So I can go ahead and open that project, and I open projects by their respective parameter file. So if I then go here and I look at recombination sequences, we should see recombinations. And so our run was successful. And what we need to do to get our haploblock determination file is go to Tools at the top here, go to Export, and then say Export haplotypes blocks file. And I will get a window, and that window is going to ask me where do I want to save it. And for me, it's okay if I save it in the FlexQTL results folder. So I'll just say select this folder, and at that point, I'll have created two files. One is one with the double recombinations, and one is with the haploblocks. I want to point out, if you get this file and you start looking at the M-consistency file and the double recombinations, there's still some double recombinations in here, and there's still a few parent-child errors. It's probably because I took this file from a clean file, but then I changed a few things to make sure I'm only sharing data that I can share. And somehow, somewhere, a few errors got in. At this point, given that I've gone through the whole curation in Apple, I didn't really have time to go and fix those few errors, but normally you would have to make sure that those errors are not there, just in case if you're looking at this folder. But then Visual FlexQTL will now have created this haploblocks map file, and I will open it, and so you can see what it looks like. And so it looks like this, where you have a column with your markers, a column with the chromosome and the position, and now also for each marker indicating to which haploblock it belongs. So you can see now here that all these markers here belong to haploblock 1,1. So this is the first chromosome and the first haploblock on that chromosome. So all these markers are grouped together in a single haploblock, and then the next haploblock is even bigger. And then the file continues defining the haploblocks. So now we have our haploblocks determined. So now for all of the group markers, what we want to go and do is determine what are the alleles or what are the haplotypes for each haploblock. To do that, we need to run another FlexQTL run. Important in this run is that we keep our pedigrees truncated. So we keep those intermediate ancestors, we keep their parents missing. But at this point, we want to remove those dummy offspring again. We have determined our haploblocks. Our selections have been taken into account, so we don't need them anymore. And from experience, if you keep them, because they're all missing data and they're connected to all these parents, they'll somehow, during this whole process, will start adding a lot of missing data to our parents and our grandparents rather than so they're actually causing more issues now in the next step than they are. So at this point, we want to rerun FlexQTL and with the same parameters as before. And at that point, I've created a different run that does that, because again, that would take about an hour to run. So I created a different run called haplotype determination. And so if everything goes well in your run and with those parameters, then what we get is we get a few output files that we need. One, we'll need the FlexQTL parameter file from this run. We'll need this file called flexqtl.sort, and I'll open it in Notepad so you can see what it looks like. So this is, as you might see, this is just another data file. This is actually, so it starts with a population, then an individual name, then the two parents. In our case, we had one nuisance variable and one phenotype variable, and then all the alleles. The only difference with this file and our data file is that this one has been sorted, and that's why it's called .sort. And it's sorted in a way that parents are always higher in the file than their offspring. So here we have Delicious, and so Delicious has Winesap and father of Delicious as parents, and so they're above Delicious in this file. And the same goes for Golden, which has its two parents right on top of it, and then Splendor has Golden and Delicious as parents, and so those both are also. So this is just our data file, but then sorted in a very specific way so that parents are always on above or on top of their offspring. And then we need one other file, which is the haplotypes file. And the haplotypes file looks like, it's to open. What it holds is our phase data. So we need phase data because we need to know which alleles are on the same homolog and which ones are not. So it starts with some explanation about the file, and you can see that they're all they all start with a semicolon, which means that, well, FlexQTL and even Petty haplotyper that our software will ignore these lines. And then it has the chromosome, the position of each marker, the names of the markers, and then for each individual, there are 5 lines in this file. The first 2 are hap1 and hap2, which are our 2 haplotypes, or the 2 alleles, or the 2 homologs of the chromosomes, and then saying which alleles are on each chromosome. Now, the first individual had missing data, so nothing is filled in, but the second individual, WINSEP here, did have data, and so we can see that across the markers, across chromosome 1, it has determined by phasing that allele A is linked to allele B, is linked to allele A, B, and so forth, and that the second homolog is BA, and so forth. Now, in the case of WINSEP, we don't have the parents. In the case of Delicious, we do have its 2 parents, or we have 1 parent and then the father of Delicious. And so in this case, once we have the 2 parents, haplotype 1 is saying which alleles are coming from the mother. And so in this case, that would be WINSEP. And I'm trying to, if I highlight it correctly, you can see that this one should be corresponding completely to the one it's getting from one of the 2 that it's getting from WINSEP. And in this case, it's the top one. And then the second homolog must have come from the father of Delicious. And even though we don't have data for that one, once we know one homolog and we have the full genotypic data, we can determine what the other homolog is. Now, the second and the third and the fourth line are GPO 1 and 2, and I mentioned this briefly last time. GPO stands for grandparental origin, and what that is saying is that if this came from the mother of Delicious, which is WINSEP, then which of the 2 homologs did it come from in WINSEP? And 0 means that it was haplotype 1. So as you can see, I've highlighted them. These 2 are identical. So because it is coming from hap1, these are all zeros. If it would have been corresponding to hap2 of WINSEP, this would have been 1. So it's the same. It's that information that we get in our visual FlexQTL when we're looking at recombinations. And then GPO2 is the same, but then coming for the alleles coming from the father. And then the last line here is the probability, and that's the probability, I believe, that that a certain phase was assigned. And you'll see a lot of missing data and a lot of 1s most of the time. So that's how our file looks like, and we'll come back to that file once we have haplotypes. But this is our phase data that we use to determine haplotypes. So we have the haplotypes, we have the FlexQTL parameter file, and we have the FlexQTL sort file that we want from this run, the run that we still truncated our pedigree, but we removed our dummy seedlings. And then we had from before, we have our haploblock definition file, which was this one. So we have now all the data we need. And then what I do is I copy all that information in one folder, which is the haplotypes, the haploblock definition file, and the 2 FlexQTL files, or parameter file and the sort file. And then we need to run Petty haplotyper, which will define our haplotypes for us. And that's an R package, so I'll go ahead and open R. And so Petty haplotyper is an R package. So the first line of this code is just telling R that it needs to load this package. Now, if you don't have this package installed yet, you have to install it. And so you do that in RStudio, at least under Tools, and then Install Package. Now, Petty haplotyper is not deposited on the repository of R, so it's not available online. You need to download it either through their website, but I shared it with you in the folder. And so at that point, once you have a package already on your computer, you can say, rather than choosing it from the repository, say that you want to have it from a package on your computer, and then it will ask me to show that package. And so when I put it on Dropbox, it was under software, and then under our packages, then Petty haplotyper, and then it's this .tar.gz, which holds the package. And then I would go ahead and say install. And then the only other thing that one needs to do with the code is this single line, and that will start then making our haplotypes. So there's two things you can change here. The first is a session ID, which is just a name that will be given to all your output files. So in this case, I could, for instance, call this Apple CRS, because that's the data set we've been working with. So then I know that are the haplotypes for the crop reference set of Apple. And then the map file, I need to say what the map file is. And with map file, they mean the haploblock definition file. So if I didn't change that name after it's been generated by Visual FlexQTL, it's called haploblocks.map. But you can change that name. You cannot change the name of the other files. So if you use this code, it is expecting an mhaplotypes file, a flexqtl.sort file, and a flexqtl.bar file, and it will expect those names. But you can change your map file, so you can, as you're changing your haploblocks, you can keep track of where you're at, and so you can change your map file. And then you would just go ahead, select these two, and click on Run. Now, for those who know R a bit, you can see that my R is still running. It's actually doing one of these parenthetic checking, and it's still running. And given that it's pretty far in, I don't want to cancel it, because otherwise I'll lose days of work. So I won't run it right now, but I can show you what it looks like if you do run it. If you run this, if you run R, it will say it's reading the data files, and then for each of the haploblocks, it will start defining alleles or haplotypes. It will say how many alleles it defined. Then once it's done through all of that, it will start looking and make sure that it will see if it can consolidate alleles, and I'll come back to that in a minute. It will consolidate alleles, and it will check whether alleles are consistent between parents and child. So it's doing some parent-child checking. And then once it's done with that, it will write all the output files. Now this, again, I think takes about 2-3 hours. So again, I wouldn't be able to show you the full run during this session. Now, what do I mean with initial alleles and consolidating? Well, my understanding, when Petty haplotyper starts, it will look at our haplotype files, and whatever is there, it will use that as the initial allele. So if for our first haploblock it was AABA, then it will say that's my first allele, and it will give that a number. And then if the second individual has AB missing B, then it says, oh, that's different than the first one, so I'll give that a separate number. And it will do that for all the alleles it sees. So that are the initial alleles. Now, some of these alleles are actually identical, it's just that they have some missing data in them. And so what Petty haplotyper will then do is try and make groups of unique patterns and then consolidate those. So if you see that right here, Petty haplotyper initially identified in this example 7 alleles, and the first is AB-B, and the second, the fifth is AB-, and the seventh is -B-BA. But they're all sharing a common pattern, and the common pattern then overall would be AB-BB, -BA. Whereas this individual is AA-BB, and so this the second A here is already not matching any of these B's, so it's a separate pattern. So it's put in a separate group. And then you have a few patterns that cannot be grouped uniquely. For instance, this first pattern can be grouped to both, can be included to both groups, so there's no unique way of assigning it to a group. So petty haplotyper will do this process and as such consolidate alleles. And then secondly, it will be looking at parent-child relationships, because if this individual is the offspring of an individual that has this, and that individual does not have that, the parent does not have that, then it must mean that this came from this group. And so it will try and consolidate as much using pedigree information, the alleles, and so reduce the number of alleles that are there and fill in as much missing data as possible. Now, you might wonder why there's so much missing data. We should have excluded SNPs with missing data. It's not necessarily that the SNPs have missing data, but in some cases, when we phase our data, we cannot accurately determine the phase. So rather than randomly saying, well, it must have been the A allele or it must have been the B allele that are on homolog 1, at that point, when we did the phasing, Visual FlexQTL will just have said, I don't know on which homolog each allele is, so rather than just guessing, I'll make it missing. So it's not missing data as in missing SNP data, it's missing as in I couldn't, Visual FlexQTL could not initially determine the phase properly. That's one of the other reasons we add the flexqtl.sort file, which is the full SNP data, so that as petty haplotyper is making assumptions and checking phases, it can look at the full SNP data and make sure that whatever it's imputing and filling in is correct, is matching with the genotype. So once we've run that run, which is about, like you said, about 3 hours, I think, at least for the data set I've been working with, we get a whole bunch of output. And actually, there's a lot of this output I never use. So you can see already all of these files have the apple_CRS start with that, and that's because I gave my session ID as apple_CRS. And then you can see a whole bunch of named files that start with final, and you can see a whole bunch of files that starts with original. So all the ones that started from original are files that hold the data from that initial run, from that initial allele determination. And all the ones that are final are the ones that it came up with at the end. So overall, I'm not really interested in what it came up with in the beginning. I only want to make sure that I want to know what it came up with in the end, after it did its full analysis. And then for both groups, there is a set of files that has final HB, and there's a set of files that have MRK in them, both for the final files here and for the original files here. So MRK stands for marker. So those files just hold our original marker, our original SNP data, whereas the HB stands for haploblock, and they hold our haplotype data. And so I'm mostly interested in the haploblock data rather than the marker data, because that's what I started with, and I want to have haploblocks and haplotypes now, and not marker data. So, and then there's 4 files here. The first is a .ped file, which is a PettyMap file. So for those who are familiar with PettyMap, you can use this as your input file for PettyMap. But for data curation, I haven't really been using it. And then we have 3 files, which are called flexqtl.dat, map, and parent. By now, these files hopefully look a little bit familiar. So what these are three input files for flexqtl, so that we can rerun this data in flexqtl and find any remaining errors. There's a few other files that are here. The messages is just a summary of all of this, or it's just showing everything that was put in R. So there's, if you want to look at that, you can to make sure everything got convergence, or if there were some haploblocks that caused an issue there. The file that I really use the most from the other files is the haploblock alleles.dat, and what that is is the definitions. It's telling us what is what. So in this case, it's telling us for haploblock 1, there's a marker count of 10, which means there were 10 markers in haploblock 1, and haploblock allele ID 1 or haplotype number 1 is this. And so you can see that 1 is just all missing data, and that's the default for every haploblock, is that haplotype number 1 just means only missing data. And then as we go further in this file, you can see that haplotype number 2 means A, B, and so forth, but there's still 1 missing data, and so forth. And then 4 and 5 are actually haplotypes that have no missing data in them. You can also see that here because the NA count tells you how much missing data there is. And so for these, it's 0, which means that it's a full haplotype or there's no missing data. So you can also see that FlexQTL keeps all the alleles it wants defined, even though our petty haplotype keeps all the alleles it wants defined, even if it was able to consolidate them after that. So in the whole process of this, petty haplotype will define 89 alleles for haploblock 1. And the more SNPs there are in a haplotype, the more it will most of the time the more haplotypes it will have defined. That doesn't mean that all of these haplotypes are in our data set. Under frequency, you can see how often it is in our data set. So you can see that there's 82 times the missing, but then you can see that a lot of these other ones that have missing data in them, they are actually not in our data set anymore. They were just defined along the way during the process. At some point, they've been consolidated. So this is an important file because once we're starting error checking, we need to have an idea what's happening with at our SNP level. So once I got this, what I do is I take these 3 files, I copy paste them somewhere else, and I start a new FlexQTL with those 3 files. Now I want to point out that one, I've said it, I think I've mentioned it a few times, but otherwise I'll say it again, is that FlexQTL does not accept anything else other than flexqtl.par for its parameter file. So the initial name was much longer, and you have to delete that whole name and just make it flexqtl.par again. And then the other 2 files are actually these 2 files, and the files that petty haplotypes are generated were pretty long names, and I've noticed that sometimes Visual FlexQTL or FlexQTL has issues with really long file names, so I've reduced those names just so that everything runs properly. Secondly, at this point, it might be a good idea to reintroduce the parents of intermediate ancestor, because by this point, everything's been phased and everything has been determined. And at this point, we do want to make sure that whatever was in some ancestor, that still matches our offspring or one of their further descendants. So it might be good at this point, or it is good at this point, to bring back in that pedigree information. And then I've barely ever had it, but I had it when I created these files, is when I load this into Visual FlexQTL and I start running it, I get an error saying that for, I think it was for 2 markers, that there were too many alleles. There were more than 100 alleles, so there were more than 100 different haplotypes for a single haploblock, and apparently Visual FlexQTL doesn't like that. Now, as I've shown you in the haploblock definition file, and you can see if it's still here, that most of the time there's a lot of these alleles that just have a lot of missing data. And they're often, not always, but often they're the really high numbered alleles too. So in this case it's not, but a lot of the times it is. So when I looked at my data set for those 2 markers, what I noticed was that all the way at the bottom, there are here a bunch of individuals which are actually not directly connected to the pedigree, and so phasing is much harder, or it's actually not really doable. But visual FlexQDL faced anyway, and Petty Haplotyper tried to make sense of it, and so it created a lot of data haplotypes with either missing data in or just random haplotypes. And so at that point, I do know that most of these are not right. Secondly, what sometimes happens, like with Prima, is that we only have partial data for that one. So there's a lot of missing data in these haplotypes. And so for those two markers where there were too many alleles, I deleted a few of these alleles off just because I know that they were nonsense anyway. And at that point, I fixed my file. So I think that is a shortcoming of Visual FlexQTL, where it cannot take more than 100 alleles. On the other hand, in my experience with our data sets that are pretty connected through pedigree and everything is related, we're not really expecting more than 100 alleles at a given time in our germplasm. If there are truly more than 100 alleles, I would suggest that you look at a subset of your pedigree that might have pretty unique alleles, and you run that separately in the beginning just to do some error checking rather than just deleting that off. And then when I'm looking at error checking, and so we run Visual FlexQTL again, and then as before, we look at the consistency file and we to find every parent-child errors. And I think I have a file here that was run, and in the end, I think this one for some reason took almost a day, which normally doesn't take this long, but but I was able to get one run in, and you can see there's again a lot of errors. So you might be taken aback a bit by these errors, but I can tell you that a lot of these are very easy to solve. So we look at consistency file again as before, and we look at all the haploblocks that have errors in them in a very similar way as we did with the single marker. Now, so I'm going to close this file for now. The only difference is that if I don't know where is it? If I start looking at this file here, and it's much harder to find errors and to figure out what is going on, because at this point these numbers don't mean anything anymore. When these were SNP data, it was A and B's, and so I could go into Genome Studio and look at the marker call and see if the SNP was clustering well, etc. And otherwise, I could make sure my calls were correct. But with our grouped haploblocks and haplotypes, it's much harder to do so because these numbers don't really mean anything unless you start translating them using that definition file. So I found it much easier to spot issues when, rather than looking at the data file, by using the new haplotypes that was generated for the haplotypes, and using that file to investigate what's going on. So the haplotype files look still the same as what it looked like for individual SNP data, but now it has these haplotypes, and so now it's, rather than saying which SNPs are in the same homolog, it's showing here which haplotypes are in the same homolog. And so what I do is I just copy this part of the table because I don't really need the rest. So I've been holding Control and Shift as always to just select everything, and then I paste it into a new sheet. I will save this as a Excel file. I think I already did this for this folder, but I will save this as an Excel book. So that any changes I do, any filtering I do are maintained as I'm doing this. And then I add 2 extra lines. I add 1 extra line here, 2 extra columns, 1 in column B and 1 for column D. And so what I will do then is what I want to do, why I do this, the first column, I want to know which is this parent that it's coming from. So as I said, this is coming from the mother, the second line is coming from the father, and again for GPO, it's mom, dad. So I want to know what these are. So the easiest way to do so, for me at least, is by filtering. And I'll first go to GPO1 and HAP1, which is selecting all the lines where things are from the mother. And then if I have my data file still open, and then now with index and match, with index, I'm going to look in the file in the column of my data file that holds the mothers, and then with match I can say to look for this individual, and it needs to look into column B for that individual. And as always, I don't want an exact match, so I put a 0 there. And then, well, the mother of this is missing, but then as I drag this, you can see that the mothers are start being filled in. And then I do the same for the father, but at that point I need to query the other column. So I'll do index, and then at this point I need to query column D, because those are the fathers. And then again, I will match it to this individual, which can be found in this column. And again, it must be an exact match. Now I can't really drag this, because if I unfilter this, there's already a bunch of cells filtered in. So I can't double click on this. What I have to do is just drag it, because if I double click, it will just change my formula. But that's not too much extra work. And then all my parents should have been filled in. And at that point, I do want to also go in and look at the probability row, which is not attached to either, or it's attached to both parents, not to just one. So I'm not going to fill in either one, but I'm just going to make sure there's something in this cell, just because it makes it much easier to select things in a column if all cells are filled in. And then the last thing I do is just copy paste this with values so that the formulas are gone. And so at this point, right now, when I'm looking at this data, I know now that, well, the first column in delicious is coming from WineSap, and the second column is coming from the father of delicious, and so forth. The second thing I do is I don't really have to, I paste in a single name, any name is okay here, and then I use the formula equals if, then or, and then what I want to do is say, well, if I want to look up a specific individual, I just type the name in this cell, and then I want to find that individual, and I want to find all of its offspring. So what I want to do is check whether this cell is equal to this cell, and to make sure it always stays in A1, I press F4 so that there's these dollar signs that lock it into this cell. And then I say, well, I don't only want to find this individual, I also want to see if it's an offspring of this individual. So it's either this or the parent name that must match this cell. And again, I want to make sure it stays in A1, so I make sure there's dollar signs attached to it. And then I say value if true is 1 and value if false is 0. And if I then drag this formula, I can now easily get all the rows that have WineSap either as itself or have come from WineSap. And now when cleaning up the haplotypes, I only need to look at the haplotypes. So I'm only gonna select haplotype 1 and 2. And what this does is now I can see what the two haplotypes are for WineSap every time, and I can see what all of its offspring got. So if something is not matching there, I would more readily see that. And a better example is Golden Delicious, because I think so I have to refresh the filter, and then I can already see that there's something going wrong here, because the values for Golden Delicious have been made missing. And then if I look at the offspring, I see offspring with 6, I see offspring with 7, but I see one offspring with number 31. And that's when FlexQTL will report an error. And that is because, well, if most of the offspring have 6 and another half of the offspring have 7, then we expect Golden Delicious to be 6, 7. But there is one individual with a 31, which is not matching either of the parental alleles. So at this point, I just need to know that I need to start figuring out what's going on with this 31 allele, especially because it's only occurring once. And so by using this file and this setup, it's much easier to get an initial idea of which individual is causing a problem. And what I need to start looking at. And so at this point, I will need to go and look in more detail what this 31 means. So there are two main, I'll go back to presentations here. There are two main things that happen. The first is, as we've seen with the 31, this is another example. All of the offspring of golden delicious is either 4 or 5, but there's one individual that has a 6. And golden delicious is supposed to be 4 or 5. So the 6 is off. And so when we look at what 4, 5, and 6 mean, SNP allele-wise, we can see that actually 5 and 6 are actually identical, except for this allele. In the 6 it's missing, and in 5 it's a B. Now, I've also colored up this file already a bit, where I colored up the top line of golden delicious as green, and the second line of the second haplotype of golden delicious as yellow, and then I can also color the individual based on which one they inherited. And so you can see that this individual is all green, this individual is all yellow, and this one's all yellow except for this one red where there's an error. But we can see that both left and right, it's yellow, so it's very unlikely some weird recombination happened here. And so what is the case, as I check the genotypic data, is that this 6 allele is just the same as 5, it just has a missing data, so I can safely go in and change this 6 into a 5, and by doing so I resolve my error. So a lot of the errors you'll get reported are like this, and actually you can just improve your data and remove missing data by filling in the correct haplotype there. But you will have to look up what these are. And then the second thing that I've seen the most is where, again, we have a 6 here, and it's 4 or 5. This time the parent is Splendor, which has a 4 and a 5, and its offspring has a 6. Now, if you look at the color code, you might already start seeing what's happening. Again, the top line is green, and the second homolog is yellow. But in this case, everything left of this marker, or this haploblock, is green, whereas everything on the right is yellow. So it means that a switch occurred from the top line to the bottom line, which means the recombination occurred. Now, if we go and look at the definitions of these three files, these three haplotypes, we can see that 6, well, matches both of the haplotypes in the beginning, but then here has an A, which matches the top allele, the green one, but not the bottom one, the yellow one of its parent. And then at the end of the haploblock is a B, which is matching the yellow part of the yellow homolog, but not the green one. So what happened is that it switches from green to yellow here, so which means the recombination occurred either between this marker and this marker, or between this marker and that marker. So the recombination happens somewhere in this interval. Now, if you see that, there's two things that can happen. One is that the recombination occurred in the seedling, and at that point, yeah, it's causing an inconsistency, but it doesn't really matter. You can leave it like that, or you can make the data missing if you don't want to have all these errors reported. But you would just know that you could mark it somewhere down that if you get that error again, that you know that, no, actually it's okay, it's just the recombination happening in my seedling. Now, in this example, Cyrus is not a seedling, it's a cultivar, and we wanted to have our recombinations, we wanted our haploblocks to be free of recombinations for selected material. Now, for this individual, this selected individual, a recombination occurred in its haploblock. So at that point, we need to go and adjust our haploblock borders. And the easiest way, or the best way to do this, would be to split up this haploblock into 2. And there's, in this case, 2 places to split it. You could split it into the first 3 markers and then the last 2 markers, or you can split it in the first 4 markers and then the last single marker. Now, I don't really like that. There's not a correct and a wrong way, but given that I'm trying to group my markers, I'd rather have a haploblock of 3 and a haploblock of 2, which is still more informative than if I had a single haploblock of 4 and then the other one would just be a single SNP rather than really a haploblock. So when I was splitting up, I would split it here, but it's according to what your preference is, I guess, or what your goal is, that how you would split up this. So what I do is then I open my haploblock file and I rename my haploblock for the markers that or for the haploblock that needs to be split up. And so in this case, I had to split up haploblock 119, and these 4 markers had to make a new haploblock. So rather than giving it, well, I could name this now haploblock 120 because it came right after 19, but that would mean I have to change almost all my haploblock names for the rest of the chromosome. I could also give it a higher number, one that doesn't exist, but that would be confusing because you might think that the haploblock is then near the end where it's not. So what I did is if I split up a haploblock, I called one of the 2 resulting haploblocks, kept the original name, and the other became an A, or if I had to split up it in multiple groups, I would name it A or B, so that I knew that originally it was still haploblock 19, but that now it has become a different haploblock. And I would also keep track of that in a separate column, just to be sure. Now, at that point, I will have to rerun PADI haplotyper with the updated map file, because my haploblocks definitions have been changed, and I need new haplotypes for both the 2 new haploblocks. I don't really need everything else to be rerun. I also, when I'm doing this, I don't really need a new data file, or don't need a new sort file because my data has remained the same. The only thing that changed was my haploblock definition. So I can use most of the other output files I created. I don't have to rerun everything again. I just have to now run PADI haplotyper with a new haploblock file. And so again, why did this happen? Well, it happened because, as I was saying earlier, it's just choosing its splitting point in the middle, and if there's already one, it will not create a new one. But it's not necessarily because a recombination happened here that it must also have happened here. It could very well be that these 2 recombinations happened in different locations, and so at that point we would need that extra haploblock. So that's why you will see occasionally that you need to split up a haploblock again. And then what I do is I keep track of all the haploblocks I need to redo. And so in the case of this one, if I split this one up, I would have to say it's 19 and 90A because it's the original 19 that got split into 2 new ones. There are some cases where I only need to change, where I don't split up the haploblock, but where for instance, I found issues still with SNP calling and I changed all my SNP calls. At that point, my haplotypes will change too. At that point, I only need to redo that one single haploblock. So that's why you see in this list, you see some that are 35 and 35A that come in pairs, and others are just individual. And that's because for those ones that are only there, like individual, that don't have an A or B partner there, it is because I changed something to the SNPs in that haploblock, but I didn't split up the haploblock. So I keep track of which ones I have to redo. And I do that because once I'm working in the mHaplotype file and I'm changing things, well, I looked at those and I've changed that. If I would rerun everything again, all those changes I made might get lost. I don't want that to happen. So what I do is I rerun everything. I rerun PADI haplotyper, I run a new Visual Flex QTL run, and then from the new mHaplotype files that then arises, I only take the data from the haplotypes I need to redo. Whereas all the other ones, the ones that I've already fixed and that I don't need to redo, I just keep them from my old file because I know I fixed them and I don't want to go in and fix them again. So that's why I keep track of which ones I have to do again. Now, the other thing, and maybe I should go out of the presentation for this, is that I want to point out, if we go back to the input files that we used for PADI haplotyper, which are these, is, as I said, if we just split up a haploblock, then it's only this file that changes because it's only our definitions that change. Now, in a few rare occasions, I have to either redo SNP calling for a single SNP, or I decide that the SNP is so bad, actually, that it's so messing up the haplotypes, I want to have it removed. At that point, not only does my map file changes, but also my sort file and my mHaplotype changes, because I've changed SNP calls and I either have deleted SNPs. So at that point, those files change as well, and I will have to rerun do one extra Visual FlexQTL rerun where I recreate the haplotype file, I create the stored file just with that improved SNP calls or without the removed marker. So at that point, you would have to go back and rerun a few more extra things. But again, I would then after that, I would only keep the haplotypes that I indicated that needed to be looked at again. I would only use those data from the new run, whereas I would keep my haplotype files as I've created here with all my changes for any marker that I'm confident that I solved. I think that, so let's see what time we have. Okay, so these two examples that I've shown here, the one where a haplotype just has a missing allele in it, and the one where there's a chain where there's still a recombination in a haploblock, those are the two issues I've seen the most. And so only this would require rerunning. I think overall I changed maybe the calls, or I deleted SNPs for about 5 or 6 SNPs at this stage, because normally by this stage you've more or less fixed everything on a single SNP level. I think there was one time where I had to reorder markers as well, just to make sure that the haplotypes worked. When I did that, I would also have to go in and rerun with the new map and then update it. But those are more exceptions than the rule. So normally, what I did is I went over all my haplobloks and I just made sure that my parents were consistent with their offspring, and at that point, after I did all of that, I created a new data file based off this haplotype file, and I rerun it again just to make sure I truly solved everything. Now, if we did bring back in that pedigree information that we removed, there's a few other things that might have happened. For instance, I was telling you earlier that if things are not connected to the pedigree, their haplotypes might become nonsense. And we can see that clearly here with McIntosh and Wajcik. And well, for who's not familiar with this, Wajcik is a sport, so it's a clone of McIntosh, so they should be genetically identical. The only difference is that Wajcik has a columnar growth, and that's because there's a very specific deletion somewhere in the genome, I believe, or an insertion somewhere, which causes the trees to grow as a column rather than having a normal branching pattern. But otherwise, they're exactly genetically identical, so we expect our haplotypes to be identical. Now, McIntosh has a bunch of offspring in the data set, Wajcik does not, so it's completely disconnected from the pedigree. And so as you can see here, rather than being identical, all the brown ones are places where things are not matching, so haplotypes are not even matching, whereas the green ones is at least it's matching, but the green ones are all on one homolog, whereas in Wajcik it's just jumping back and forth because it can't determine accurately which alleles are on which homolog. So just be aware, if you have something that's completely pedigree, not connected to anything in the pedigree, your haplotypes will probably not make that much sense. Now for McIntosh and Wajcik, the solution is simple, because given that they're genetically identical, I can just copy the results from McIntosh and paste them for Wajcik. Another example is here where I had Venda and Rubin, which I showed earlier, where I told you we do know the parents, but we don't have this data, and we cut them out during the haplotyping. And then when we did the pedigree checking afterwards, with the haplotypes, we put the pedigree back in. So you can see that both of the parents of Topaz are missing. We don't have data for that, but for Rubin, for the father, we do know the two parents of that one. So we know the grandparents on this side. For the other side, it's a bit more complicated, but all the ones in green, sorry, we have data for, and all the red ones we don't. But you can see that eventually we have data for all the ancestors of Topaz. And at that point, we do know that any haplotype we see in Topaz must be present in either of the ancestors, because Topaz must have gotten that from them. And so if I looked at the haplotypes for Topaz, that was done mostly correctly, even though it wasn't really pedigree connected to anything. there were a few that I had to adjust, where I had to do the phasing manually and fill it in. And so what I did for each of the for the haploblocks where it's not matching, I was always just making sure that in Topaz, the alleles that I saw in Topaz were present in its ancestors. And if that was not the case, I knew I had to fix something. And it's not just that they had to be present. I know that one of the two alleles must have come from the father side, so from Lord Lambourne or Golden Delicious, and that the second allele must have come through the mother side, so either from Spartan, Lord Lambourne, Jonathan, or Piri 1426. So by doing that, there was actually always only one combination possible of ancestral alleles. So that required a little bit of extra cleanup, this individual, but that was because it was not really connected to the pedigree, but I could fix it because I had pedigree information and parent information. But those are very specific individuals that will require a bit more of your time if you want to have haplotype data for those individuals. Another case is where we have M. floribunda. So in this case, in Topaz, we were not able to phase Topaz, but we were able to phase all its ancestors, so we could work from the top to the offspring. In this case, it's the other way around. We didn't have anything for M. floribunda, which is an ancestor of this individual, which is a grandfather of this or grandparent of this individual, but we could correctly phase this individual. And we also have all the other grandparents of this individual. So I could go in and look at this phased individual, this haplotypes data, and see where it was matching with its 3 other grandparents. And every time it didn't match with any of its 3 other grandparents, it must have meant that it got a stretch from floribunda, the 4th grandparent. Now, some of the haplotyping in M. floribunda was also nonsense because, again, it was not connected to the pedigree, but at least for the stretches that we are sure that came from floribunda, I was able to phase and determine haplotypes properly for floribunda. Unfortunately, not for everything, because this genome was not really fully represented in our data set. And then as another example here is Lodi that we made the data missing for because it was low quality, but we did have its parents and its offspring. And so we were able to start filling in a lot of the data because we were able to phase its related individuals properly. But a lot of these cases require a bit of manual phasing and fixing the haplotype. So it depends on how important these individuals are, if you want to just have them data missing or if you want to fully phase them. Now, for these individuals, for Lodi, where we had 2 offspring, we could already just based on the offspring fill in a lot. For instance, in this case, the two offspring, early Cortland and Ginger Gold, were showing different haplotype patterns. So at that point, we knew that Lodi must have gotten these 2 haplotype patterns. Now, at this part of the chromosome, they actually share. The 2 offspring share a haplotype pattern. So at that point, we don't know if Lodi was homozygous or if a recombination occurred, and they're actually inherit both the same segment. So at that point, we only filled in 1. And so what I want to show here is that if you have enough offspring, you can just start filling in a parent, even if you don't have data for that parent. And you might not be able to fill everything in, but you will be able to, well, if you have 1 offspring, you will be able to fill in 1 full haplotype stretch, 1 full homolog, because that individual just got 1 full chromosome sets from its parents, so you can fill in that. And once you start getting more individuals, you'll be able to fill in more parts. And the paper that describes the creation of this germplasm by Karen, somewhere it states that if you have 7 F1 seedlings, there's a 99.2% probability that a given A allele of a parent is present in at least 1 seedling. So that means that once you have 7 seedlings, there's a very, very high chance that you'll have both alleles and that you can fill in both the missing alleles for the parent. And it's definitely at a haplotype level, it's relatively easy to do so. So that's already partially an application of haplotypes rather than data curation. So as you're looking at your haplotypes and the errors you're seeing, you want to first again use the M-consistency file and figure out all the Mendelian inconsistent errors. And as I said before, it will mostly be because of missing data in a haplotype or because a recombination occurred within the haploblock. Once you've done that, we want to, again, make sure there's no suspicious double recombinations. From my experience with Apple, I think at this point, I found 3 suspicious recombinations or so. It's really low by the time you get here because you've been doing so much error checking that by the time you get to that next step, there's really barely anything left anymore of errors. So that was maybe half a day of work. Then once you've done that, there's really not a good way anymore to find errors in your data set. And I think we can assume at this point that our data set is very clean and that there's either no or a very minimal amount of errors left in our data set. So at this point, we can just start using our haplotypes and make lots of great discoveries and be just very confident in the results we get because we know our data is really, really high quality. Now, it might be that if you are looking at a very specific region, at some point you might still find 1 error or so. But overall, this is very high quality genotypic data set. Now, I can't really show you, unfortunately, because my R script is still running, so I can show it to you next week. I've been saying in these slides, well, I looked up the haplotype definition, and if you remember the file that has it, which is this one, this is a pretty big file. And so looking up all these haplotypes, alleles, and comparing them, it just always takes a bunch of time. And when I was talking later about manual phasing, you need to look at the genotype, and you need to figure out which haplotypes there are and which combinations are possible. Now, if you all do that all manually, that takes up a lot of time. So what I did is I created a few small R scripts that do it for me. And so there's 5, and I can show them next week, but there's 5 functions I created. One is just looking up the haplotypes. So with this function, I would say for haploblock 1010, give me haplotypes 4, 5, and 6. And I could determine any order I wanted. I could have said 6, 5, and 4, and it would report the haplotypes like this in the table, as I've shown here in the PowerPoint, and I could very quickly see what's going on. I could ask which SNPs are in this haploblock if I'm thinking there might be something wrong with the SNP, so I can quickly go and check the SNPs in Genome Studio. I could ask me what's the genotype of this individual, so I don't have to go into my data file and look for that individual and figure out what the genotype is. I could just have R report it to me. I had one function that said, well, if for this haploblock, I think it must be B null. Which haplotype is that? And it would tell me which haplotype it is. And then the one that really helped a lot, especially with the manual phasing, is saying, if I said this individual for this haploblock, I know the first haplotype is 8. And then what it reported back to me saying, well, if the first haplotype is 8, the second haplotype must be 4. And this is what the SNP pattern looks like. And so at that point, that is what I used a lot during the curation. And that R script is already on the Dropbox, and I can show it to you quickly next week, but unfortunately my R is still running, so I can't show it this week. But that is just a tool that I created to really quickly clean up the haplotypes. And as I said, it's already on Dropbox, and I will share it with you. I will show it next week as part of the applications. So if there's no more questions, then that will be it for today. I think that I'll send out another email, but if you have any questions about any of the previous sessions, if you send me an email before Monday, then I can come back to it next session as well. So if there's any more questions or things were not clear from anything of the last sessions, just ask me and I can come back to that briefly next week. Otherwise, I'll just see you all next week, and thanks for being here.